Okay, we are now on this next section, and we're going to talk about Newton's laws, or as I like to say, Newton's law. And what I mean by that is, even though they talk about his 3 laws of motion, they are all summarized in one extremely simple piece of mathematics. So let's talk about what Newton's laws are in everyday parlance, meaning just I'm going to talk about it. So the first law, and you can see this on page 29 in your textbook, the first law is that an object remains at rest or in uniform motion in a straight line unless it is compelled to change by an externally imposed force. So here is an object. Here's a rock, okay? And here's the ground. That rock will not go anywhere unless I push it with a force F. Now here's me pushing the rock. But notice I have drawn the force vector, because this is a vector. I'll draw my little vector symbol above there. And we've talked about vectors in previous class. Yes. You're going to ask what a vector is?
No.
Okay. What's your question?
Well, you're saying that rock's not going to go anywhere unless it's actually being pushed by a force. But what happens if, like, say for instance, the plane that it's on, the ground, is tilted, and the rock starts to roll? It's not being pushed by anything. It's just that a shift is happening. The ground is moving, and the rock is going. It's not being physically pushed.
Right. Well, it is being pushed. The force in that case is the force of gravity, because here, so this is the case you're talking about. Here's the rock now. There is a force. It's in this direction, and it's the force due to gravity on the rock. And we're going to get to that. And that will make the rock go down the hill. Okay? So Newton's first law, if you want to call it that, is that the object isn't going to go anywhere unless a force acts on it, or it will remain in motion in a straight line unless a force acts on it. What that means is this. Now we've got to take a little bit of a leap of abstraction or a leap of imagination, and this is where Newton and Galileo surpassed the science of Aristotle in a very direct way, because Aristotle was basing all of his physics on everyday observation. And in everyday life, let's just back up to this thing here. In everyday life, the second you stop pushing that rock, it's going to stop going, right? You stop pushing the rock, it's going to roll to a stop very quickly, it's going to stop. So it makes sense to say that for an object to go, it must have a force all the time. So when Aristotle was posed with the question, well, how do objects being thrown continue flying through the air because there's no force acting on it anymore? For example, so here's our baseball player or something, and he throws the ball, and it goes through the air. The force acted on it right here when he threw the ball, and then the force was gone. The ball kept moving through the air. So Aristotle had to answer that question, and so this is what he said. He said, okay, well, here's the ball, and you threw the ball, and some of the air gets pushed out of the way in front of the ball, and it circulates around and pushes it from behind. And this circulation of air pushes the ball through the air. It's a very, very creative answer, but it is completely incorrect, right? So it's interesting, though, that Aristotle at least conceived of forces in the same way. A force is a physical push on something. That is a force. Newton's saying the same thing. A force is a physical push on something. But this is what Newton does to answer this question about things being thrown. He says that an object in motion will continue to stay in motion unless it's acted upon by another force. But then you say, well, if I throw something, you know, it goes for a while and then it falls and it hits the ground. Well, you can explain that because of gravity, but then you could say, well, if I shoot a bullet, the bullet eventually slows down and it will fall down, you know, and it'll slow down. So what force is acting on it? Well, you can say it's air friction. So how do you know it's really going to keep going forever? Well, this is where Newton imagined things moving in a perfect vacuum. And of course, we are familiar with a perfect vacuum. It's not a Bessel or the new Auric, or what is the one we have? We have the old one, the old vacuum cleaner. Anyway, Dyson. No, the Dyson's a new one. Anyway, none of these are perfect vacuums, okay? A perfect vacuum is a place that has no air, and so a place that has no air is in outer space. And Newton imagined, so this is now in outer space, you're in orbit above Earth. There's Earth way down there, you know, North America, South America, here's Africa, here's Spain. All right, so you're floating up there, and so now he's an astronaut now, okay? And he's floating in space, and he throws a rock. That rock will continue going forever, right? He throws the rock, it's going to go forever because there's no other force acting on it. Okay? Well, yeah, right. An asteroid or a giant rock in space or a comet, well, they're usually in orbit around something. Okay, we're kind of leaving that aside. Pretend he's in deep space. He's not by the Earth. He's way out there. Anyway, so he throws that thing and it's just going to go forever. Because there's no other, unless another force acts on it, it will go forever. So that's Newton's first law, that an object will stay at rest or remain in motion in a straight line unless a force acts on it, period. Now, the next, Newton's second law of motion is, and I'm going to read it from your book, it's on page 29, and this is a big, chunky definition. The acceleration of an object is directly proportional to the magnitude of the opposed force, inverse proportional to the mass of the object, the acceleration in the same direction as the opposed force. Okay, great, got it? Good. Right. Okay,
could you repeat that one?
Okay, I'm not even going to repeat it because it's easier just to write the equation, and it makes more sense. Okay, so let's do that. So all of Newton's three laws, the last law is for every force there is an equal and opposite force. Okay? All of Newton's three laws are expressed in this very simple equation. Force equals mass times acceleration. Okay? Real simple. The equation is simple, but it takes some practice to apply the equation correctly to different situations. Let's write the terms out. Write this in your notes. Force equals mass times acceleration. I didn't spell that right. I can't spell up close. Is that right? Okay. All right. Force equals mass times acceleration. Before we go any further, force is measured in units of newtons. Why would it be measured in newtons, do you think, Michael? Right, Isaac Newton came up with this stuff. And force is in units of N. And so again, this is something Aristotle wouldn't have done, is measured how to quantify force. He wouldn't have quantified it mathematically. And this is why Newton really combines Plato and Aristotle, because Plato is all about the numbers. And you have to quantify physical things if you're going to do physics. Okay, so force is in units of newtons. Mass is in units of kilograms. And acceleration, as we stated before, is in meters per second squared. So force equals mass times acceleration. That's the equation. And we'll just do one more section today for this online part, and that will be applying that equation. So let's do that.